In this video, we are going to talk about related rates. And related rates are word problems, and we're relating what's going on with variables generally with respect to time. How is something changing with respect to time? So we could talk about a ladder that's leaning against the wall, and maybe it's sliding down the wall at a certain rate, and we want to know how it's changing along the x-axis as it moves down along the y-axis, and we want to find that change with respect to time. So because we're differentiating with respect to time, we're going to do implicit differentiation. So let's look at just how would we go about doing this. A lot of times it's going to help if we draw a picture, especially in that ladder situation I was just talking about. We need to identify all the variables that we're dealing with and where they are in relation to that picture. And then we want to express rates in terms of derivatives. And like I said, we're taking that derivative implicitly with respect to time. Identify the information we have, plug everything into our derivative, and then solve for the missing variable. So let's look at a few examples. So in number 16, we have a point that's moving along the graph of 4x squared plus 9y squared is equal to 36. So we have how the point is moving, and this is actually the equation of an ellipse. So it's moving along a path that's orbital, something like this. And we want to know when the point is at this specific spot, where x is 3 and y is 0, the y-coordinate is decreasing by 2 units per second. So they're giving us an x and a y, and they're telling us how y is changing with respect to time. Since it's decreasing, we're going to use a negative there. We want to know how fast is the x-coordinate changing at that particular moment in time. So we're actually looking for dx over dt. We have an equation that ties everything together, and in this case, it happens to be the equation of the ellipse. So let's take the derivative with respect to time. So the derivative of 4x squared is 8x, and to show we took that derivative with respect to time, we're going to multiply by dx over dt. The derivative of 9y squared is going to be 18y times dy over dt. And we know the derivative of the constant 36 is going to be 0. So I'm going to take this equation and I'm going to solve for dx over dt. So my first step is to subtract this term to the other side. So we're going to have a negative 18y times dy over dt. And then I'm going to divide everything by 8x. So we're going to have dx over dt, that's what we're looking for, is equal to, and this is going to reduce to negative 9 over 2 here. So negative 9y dy over dt over, just kidding, that's a 4x. So let's substitute in everything we know. We said y was 0. dy over dt, that's how that y-coordinate is changing, is negative 2. And x is 3. So we're going to end up with 0 over 12, which is equal to just 0. So if we were to graph this equation, you can see how this value of 0 would make a lot of sense. So I'm going to go to Desmos, and there's 4x squared plus 9y squared is equal to 36. You can see it's that ellipse here. Here's my point 0, 3. 3, 0. So at that point, if my y is changing by a certain amount. In this case, it's decreasing by -2 units. You can see how X can't really go left or right anywhere. So it makes sense that that change in X with respect to Y right there, which is that point's called vertex, would be equal to 0. So let's do another one. Let's look at 19. So 19, we have a rocket that's thrown into a still pond and that's causing circular ripples. If the radius of the ripple is increasing by 2 feet per second, how fast is the area changing when the radius is 10 feet? So if we were to throw a rock into this pond, we're going to get these circles. And notice those circles are going to get bigger with respect to time. So that's what's happening here. Now we have an equation that's going to tie all of this together. We want to know how fast is the area changing. Area of a circle is pi r squared. We know that the radius is going to be 10 feet. We want to know how the area is changing at that specific point in time. So we are looking for the change in area with respect to time, dA over dt. So let's take a derivative of our equation. We're going to have dA over dt is equal to 2 pi r and then dr over dt. And if we go back to the problem, they tell us how that radius is changing with respect to time. It's changing by 2 feet per second. So let's plug everything we know into our derivative here. We're looking for dA over dt, how the area changes at this moment in time. R is 10, and dr over dt is 2. So we are going to get 40 pi. And if we were to type that in the calculator, we could get a decimal approximation. It's about 125.664 feet per second. So now let's look at 20. 20 is kind of bouncing off that idea of throwing this rock into this pond. We want to know how fast is the circumference changing. We are still keeping the radius at 10 feet, and we still know how the radius is changing. So to find the circumference of a circle, it's going to be pi times diameter. We still know the radius is changing at a rate of 2 feet per second. We want to know what's happening at this moment in time where the radius is 10 feet. And we're looking for the change in circumference with respect to time. So remember, circumference is the distance around. So we're asking, how's that distance around each of those circles changing? Taking our derivative, we have dc over dt is equal to pi times the derivative of the diameter with respect to t. Let's change that formula before we do that. We don't have a diameter here, but we could rewrite this in terms of a radius. A diameter is the same thing as 2 times the radius. And so when we take that derivative, where you get dc over dt equals 2 pi times dr over dt. Substituting in what we know. We're going to get 4 pi. And that is approximately 12.566 feet per second. So that's how the circumference is changing. Let's look at another example. The radius of a spherical balloon is increasing at the rate of 3 centimeters per minute. How fast is the volume changing when the radius is 10 centimeters? So let's identify all of our information for this problem. We know how the radius is changing with respect to time. We know the radius is going to be 10. We are looking for change in volume with respect to time. There's an equation that ties everything together, and that's the volume equation for a sphere, and that is 4/3 pi r cubed. So let's take our derivative, and remember this is implicit differentiation. Keep the constant, bring the exponent down, subtract 1 from the exponent, times dr over dt. So you can see how my equation is going to become 4 pi r squared dr over dt. So now let's substitute in what we know. Radius is 10. dr over dt is 3. That's 1200 pi. Which is about 3769.911. And we're talking about a change in volume here. So this is going to be, let's see, we were talking about centimeters. So it's going to be centimeters cubed per minute. So that's how fast that volume is changing. It's increasing at a rate of almost 3,800 centimeters cubed per minute. That's pretty fast. If we look at the next one, it's asking how fast the surface area of the sphere is changing. So we need that surface area equation. Our surface area equation is 4 pi r squared. Now all the information is the same from the last problem. So dr over dt is equal to 3, the radius is 10, and now we're looking for how the surface area is changing. So let's take our derivative. The derivative of the surface area with respect to time is equal to 8 pi r times dr over dt. Substitute in what we know. The radius is 10. dr over dt is 3. So this is 240 pi. And 753.982. And once again, this is going to be centimeters squared because now we're talking about area per minute. So that's how fast that surface area is changing. Surface area, you could think about like how much wrapping paper it would take to wrap this spherical balloon. And then let's do 25. 25 is one of my favorite problems, the ladder problem. So we have a 10-foot ladder that's placed against a vertical wall. Suppose the bottom of the ladder slides away from the wall at a rate of 3 feet per second, and we're going to keep that constant. We want to know how fast is the top of the ladder sliding down the wall when the bottom is 6 feet from the wall. So let's draw a picture of what's going on. So here's my building, here's the ground, and here's my ladder. So I could talk about that distance being x and this distance being y. And I know I can relate everything together with the Pythagorean theorem. X squared plus y squared is equal to z squared, where z is this ladder here. So we have a ladder that's 10 foot, so that tells us what this distance is. And we are pulling the bottom, the ladder is sliding away from the wall at a rate of 3 feet per second. So that's talking about how it's changing here. So that's going to be dx over dt. we want to know how fast the top is sliding down the wall. So how fast is it changing vertically? So we are looking for dy over dt. And we want to know at that specific moment in time when the bottom is 6 feet from the wall. So this is going to be 6. First thing we got to do is figure out what this is going to be. What is my y? And that's where that Pythagorean theorem is going to come in. Let's substitute everything we know into the Pythagorean theorem and figure out what y is going to be. So I have 36 plus y squared is equal to 100. So y squared is going to be equal to 64. And if I take the square root, I'm going to get 8. So I know this value is going to be 8. So everything can be related in this equation by that Pythagorean theorem. So that's what we're going to take the derivative of. But we have to be careful here. We have x squared plus y squared, and that's going to be equal to 10 squared. What's staying constant in this problem is how long that ladder is. So that's why we're going to use that 10 squared in place of that z. So now if we take the derivative, and remember we're doing this implicitly, we're going to have this on the left, and the derivative of that constant 100 is 0. So now let's solve this equation for dy over dt. That's what we're looking for. So I'm going to subtract this term to the other side. And then divide everything by 2y. So I have dy over dt is equal to negative x times dx over dt over y. And now we can substitute in everything we know. My x was 6. Dx over dt was 3. My y was 8. And we're going to get negative 9 over 4. Or negative 2.25. And that's going to be in feet per second. So that's how that top of the ladder is moving at that particular moment in time. Notice that answer is completely different than what we had for dx over dt. They are almost always never going to be the same. And then let's look at 26. We have a weather balloon that's rising vertically at a rate of 5 meters per second. An observer is standing 300 meters from where the balloon was released. At what rate is the distance between the observer and the balloon changing when the balloon is 400 meters high? So let's draw a picture to represent what's going on. This picture is going to look a little bit different than the last one. So here's our weather balloon. We have another right triangle. This observer is standing 300 meters away from where the balloon was released. So this person is standing right here. And the distance here is 300. At what rate is the distance between the observer and the balloon changing? So that's talking about this distance in here. How is that changing? So that's going to be dz over dt. We want to know that at the point in time when the balloon is 400 meters high. So this is going to be 400. Now, we also know that the balloon is rising vertically at a rate of 5 meters per second. So that's changing, telling us how y is changing with respect to t. And I'm going to put m there for meters. That way we remember the units. So we need to know how to relate everything together, and everything is going to relate with that Pythagorean theorem again. So it would be nice to know what z is here. We know that x is going to be 300, and we know y is going to be 400. So we have 300 squared plus 400 squared. And then take the square root of that. And that's going to give us a 500 here. So at this particular moment in time, that distance is going to be 500. We want to know how is it changing at that moment in time. So let's think about what's going to be constant in this problem. That distance from where the balloon was released to where this person is standing is always going to be 300 meters. This person is not moving along the ground at all. They're just standing there and they're watching the balloon go up. So kind of like with the ladder problem, we do have a constant going on there. And in this case, that constant is the x value. So we have 300 plus y squared is equal to z squared. And that's what we're going to take the derivative of. The derivative of 300 is 0. The derivative of y squared is 2y dy over dt. And the derivative of z squared is 2z dz over dt. The goal is to solve for dz over dt, so we can divide both sides by 2z. So we have dz over dt is equal to y times dy over dt over z. Now let's substitute in what we know. And we'll solve for dz over dt. We know our y is 400. We know dy over dt is 5. And we know dz over dt is 500. And that's going to reduce to 4. And this is going to be meters per second. So what that's telling us is that at this particular moment in time, where this balloon is at a height of 400 feet, and the distance between the person and the balloon is 500, not feet, meters. It's 500 meters. Then that distance is changing, and it's changing because the balloon keeps going up, up, up. So it's changing at a rate of 4 meters per second.